Am I streaming? Hey guys. So I'm getting a late start, but the doesn't seem to be much of an audience at 1 a.m. on in the middle of Texas, and the rest of the world is probably getting just started on the day. So I'm just poking around, playing with these things and sharing what I'm learning as I go. So no big deal. Uh, Good to see some people are here. Hey, what's going on, Eddie? Hey, everybody. So I got this piece of crap today, this Elgato Stream Deck, and it seems like the unit itself is screwed up, but I'm gonna try it on a different USB hub and we'll see. But it it will only respond to the keys that are to the right of whatever I pressed before, so it's weird. That doesn't seem like it would be a software thing. Uh, so anyway, screw the Elgato Stream Deck. I have shortcuts that work reliably, more or less. There we are, we're in space. Look, we're not doing Marlin today, sorry. Today we're doing retro stuff, retro things, which is why we have this up. We'll bring that up. I'm just poking through this, looking for uh, settings to turn on the joystick. Emulator settings. Here? Is it here? Joystick? HP Turbo. No. Controller, of course. There we go. And label joystick, keyboard joystick. Yes. Okay, I think this is arrow keys by default. Hey. And remember this game? Pitfall on the Atari computer. So it has good sound. Later versions of Pitfall in the 2600 also had extra chips so they could sound better and look better and do cooler things. This is a giveaway because there's a lot more colors and things on this version. Put it away. We're not here to talk about Pitfall. Not at all. No. We're looking at some good old-fashioned Atari things. Some of my favorite elements of the Atari computer. Specifically, the AtariBASIC and its clever tokenizing system. I have written a program here, which is, I won't force you to read every line, but basically it, as you can see, has a list of every basic command in it, and it does a lot of things like go to some line based on some other line. This is what you could call a jump table inside BASIC. These are all like optimizing tricks, I guess. And then basically it's little handlers for things. And this program, if it could read memory where there was another program, it would print its listing. But since it's the thing in memory when it's running, it ends up printing its own listing out. So this is what it's doing, is it's meant to be my first preliminary journey into figuring out how the tokens in BASIC are arranged and how they work, and what they are correspond to. And I was doing a little bit of guesswork, but this actually is really well documented in some various places. So you can see I have these these tables here. You could say each of these lines prints something and then returns. So these are like, jump tables essentially. Lookup table does because in BASIC you can say go to some line plus some variable. So that's always been handy to be able to do. So this is where in line 2010 I have argument tokens go to 2000 plus B, and B is always at least 14, so ends up going here and down. And then some of these things I have stop lines in because I think they're not supposed to ever happen, or I haven't figured out what they're supposed to do, but most of these are defined. And then there's a difference between whether you're reading like the first token in a line or if you're reading subsequent tokens in a line, because the first token is going to be some command in BASIC. It's not going to just be x plus 5 or something. It'll be let x equal x plus 5. So even though the first thing in a line might be a variable, it's actually a hidden let statement that you don't see. So there's, some cool tricks. So if I run this program, just to give you a demo, I've got to turn the right build system back on. AtariBASIC build. So this is going to open it up in AtariBASIC and run it very quickly. I will slow it down. So it's running in turbo mode, as you can see. But I've got it set up in a mode where it's printing out like all the tokens and then what follows. And if you look at it, it's really messy. Like you can't quite make out what's going on. Some break here. F6. Oh, I went into the monitor, so we'll just have to kill this. The monitor, I think if I say, go into the monitor and I say Control C, oops, Control C, canceled, it automatically kills everything. So let's come back, bring this back, and we'll skip ahead. So first thing it does is it prints out all the variables, variable tables, and the variable value table, and then starts out with the listing. So there's a lot of mess going on here, but F6, there we go. Is that the right one? F7? There we go. Okay, so here we have, so if we'll use this cursor as our pointer, because my pointer doesn't work on top of the window. My mouse pointer has to float around it. Oh, it's disappearing. There it goes. So we start out with something like the offset or the values that are there. So this is line number 0, and it's in parentheses. Hey, I've interpreted this as line number 0. 79 stands for the next line is going to be that far away and that many bytes, 79. I forget if it's hex. I guess it's probably hex. So that's going to be just short of 128. 6 views, 122 bytes, something like that. 123, and then the next statement is 10 or 16 bytes later, and next statement. And so that's the first bytes that has inside of a basic line. You have the binary coded decimal line number followed by the offset to the next line followed by the offset to the next statement, because you can separate statements with colons. Then you've got the statement 14 here, or 14, which is 20 probably in hexadecimal. And it's been identified as a dim statement, and then it looks at AF, and that means it's looking at this variable, Z, and then there's a token for that means, Z is a dimmable array, so it has a parenthesis after its name. Then you have 39, which is a real parentheses, I guess, or it's been interpreted as S, or let me think. Well, anyway, it gets kind of in the weeds after a little while. The next thing is OE, which means this is going to be a decimal, binary coded decimal number of some kind, and it's not binary coded decimal in the sense of like 0010. For line 10, it's going to be binary coded decimal in the long sense, or actually binary coded floating point, you could call it. You can call it a very simple floating point. It's this type here. So this is so this is going to be some number, and if we look at the listing, we can see what that number is supposed to be. So looking at line 0, if there is a line 0, let's see. I guess I probably appended a line 0 at the end. Yeah, I did. So the line 0 that it's looking at is this one here. As you can see, it's dimming Z. That means it's creating a space for 5 numbers. And in AtariBASIC, every number is one of those 6-byte binary coded decimal numbers that you saw, 4005, blah blah blah. And then I'm setting them to some values, 1, 2, 3, 4, and 5. So this is what the line is ultimately. And it looks like I might have misinterpreted something in it because it says error a couple of times. On the other hand, maybe it did get interpreted as an error because of the way that I did it. So if I'll just clear the screen. Graphic 0 is the trick you use to do that. I'll do a poke A2 0 to make the left margin 0, and then I will list line 0. And it looks like line 0 is fine. So why the program is acting up, I'm not entirely sure. It may be just I didn't quite get it right as far as these types of numbers, and that's why I was working on them at the time. But most of it works. Let's find the interesting line is there's one that I can turn on do hex. I can set do hex equal to 0 by changing line 102. So if I change this number at the end, this is just there's a lot of little optimization tricks in here if you're familiar with AtariBASIC at all. Just to like make the program a little smaller and maybe run quicker. Instead of having something that's like a list of numbers, it's, as I did here with dim z5, z0 equals 1, that one equals 2, that one equals 3. Each time you do that, each of those is going to be represented by like a big 6-byte number. You don't have that much to work with, so each of these things in the data statement is just a single byte, 0, 1. Each comma is also a byte. It costs that, but that's less than the 6. And so, you know, by the time you've used up 6, you're already 3 values here in the data statement. So it's pretty good economy. So if I run this again, my listing might look a little better. Yeah, so here it's listing out the vars, and I'm doing it slower so you can actually read it. So it finds all the variables in the variable table, then it shows the values, or at least reads the value table. It tries to figure out what the values are, and it's reading back some things there. And now it's doing my listing. Yeah, so there we go, line 0. You can actually read it. It looks like, yeah, dim z something 5, so the parentheses, the opening parentheses, I put a letter after each one because there's a few different kinds of opening parentheses. So scalar, I think, is probably what that opening parenthesis is for. It's expecting a scalar value inside of that to be evaluated, essentially. Yeah, and here, CHR string C, so that's an opening parentheses for a CHR string there at line 100, as you can see. And so you can see this is slow enough that you can kind of follow what it's doing. And it is very slow because finding the tokens in the table and all that is like, it's kind of a slow procedure. I could have built maybe faster ways of doing this, but I just wanted to have it run quickly and just get the point across. So it's working. What I would do as I was working on this is I would run it until it would break, and then I would figure out what I was missing, and then I would look and see what token it was choking on and say, oh, that must be that value, must be this token, and I now know what it is. But yeah, there's a lot of well-documented stuff about this. You can just Google it and find AtariBASIC tokens and stuff. But I am still writing this detokenizer, and I'm also doing one. Control C is not going to work. Let me hit F7 to break. There we go. I can also get this out to Sublime just by listing it out to the printer, and this will give us a long listing that's also colored. So there's yes, there's 0 is there, and I'm going to change the view, so, and a couple other things. First thing I'm going to do is close AtariBASIC. Then I'll just change the view real quick so it's not wrapping. And we can take a quick look at this program, which is, is huge, but I'll just run through the basics of it. 0 is our test line, so that was one that we could see was actually doing properly, getting listed, so I don't know, maybe when it was in that other mode with do hex set to 1, like that, it didn't like it. We'll see. But anyhow, so the first thing we do, and this is an interesting thing, optimizing thing in AtariBASIC, if you do go subs and things like that, or even go to, or whatever, it goes through the lines looking for the line that you are looking for. So it'll say, oh, is this the line, so you say go to 100, it'll say, okay, it'll start at the top, oh, there's this line 100, no, what's the offset to the next line, I'll add that, and then do this line, and then add that next one, do this one, until it finally gets down to 100. So if you do a go sub or anything like that, it's a good idea to first off not put a bunch of rems at the top of your program, or get rid of them when you're trying to make it run fast, or use one of those compilers or whatever. There's a few of them out there, or just turn on turbo mode, since we can do that now. But running on a real Atari, you're going to want to do something like, you know, compile it in down, or add assembly for the things that need to be fast. But in AtariBASIC, one of the tricks is you just put things you need to run quickly at the top, and that way, so for example, line 20 is something that it gets go subbed a few times, so I just put it at the top so that every time it go subs there, which it prints a hex number, 2-digit hex number, so every time it goes there it's quicker than if it didn't. And line 21 is return, because there's an if statement here, and this is also like built around that do hex variable, so that's like I use it for debugging. So the do hex prints out this and then also other extra info, so that's what that's all about. So yeah, it returns. So the next thing it does is it clears, which just clears the variables if I happen to use, for some reason, go to 1 or something like that. I want to clear all the variables. Clear has a space after it, I noticed, but natural just has a natural space, but that can be removed. Poke 82 0, that just makes the left margin 0. CHR string 125, that actually clears the screen. CHR string is a character, you know, like it's going to print the character that is the ASCII character 125. In this case, 125, it clears the screen. If you were to print an escape character just before this one, it'll actually print out the clear screen character, which looks like a little like UU thingy. I can show you that at some point perhaps. But yeah, so set color, you know, is just, I think I put that there just to test the listing, so it's not probably doing anything, but it's just a command that sets some colors. Color channel 1 sets 2 to something, it sets it to 2 and 15, which I forget is what. The palette and the brightness, I forget, but I'll look it up. It differs depending on the graphics mode that you're in, and in text mode it probably sets the background color or something like that. Again, it's been a long time since I've done this, so we're poking and learning together. So another optimization is to have some variables pre-configured, because referencing a variable inside of your program only takes 1 byte. If you're referencing a number, again, it always takes 6 bytes, even small numbers like 0, because everything is floating point in AtariBASIC, except for a few occasions, like your actual line numbers. The other numbers are floating point. You can actually type in, like, as your line number 3.7, and it'll think you're typing line number 4. I think it rounds up, I forget, but it treats it like a fine line number, because all numbers are treated equal, but some are more equal. So using these variables n0 through n9 is just, you know, you're going to use those numbers a lot, probably 0 through 9, especially 1 and 2, and, you know, the smaller ones. So yeah, so we just have a read statement followed exactly right afterwards by a data statement for those values, and then for the heck of it, I also initialize dohex here as 1 at the end. It's a good way to initialize. It's faster, it's better, smaller. And then you have, it may not be faster, but it's smaller. Do XP, and then so, you know, they've got some things like here, I've got another optimization, whereas I'm going to be calling these things a lot, maybe, so I decided I'll take these line numbers and I'll define them as variables too, and so I can say go to BCD, go to STR, go sub, or whatever. M push, M pop. So, and then you're dimming variables, in this case for holding all these things, and H string is used for hex, and you can see these lines can get pretty long. And AtariBASIC will happily interpret it up to 255 characters, even though the built-in editor will only hold 3 lines of 40, 120. You can get pretty long with these. So yeah, so let's zip down. The interesting part is really the some interesting ones. Go sub 197, go sub 197, go to 197. What the heck is that? That's an interesting part of the program. I'll just take a peek at it. It's looking at a couple of, it's peeking at a couple of things, and then it's go subbing 196, and I'm assuming it's adding 1 to A each time. So it looks like it's just reading the memory, basically, as it's going through. So it's go sub, go to, array, and then string, go sub, go sub. It treats them similarly. Yeah, there's a lot of really interesting bits in here, which if I look at the original untokened programs, probably, yeah, they're probably nicely laid out. Well, let's look at the nicely laid out one at least. The problem with this is just that everything's compressed down, so you might see a line that's like GOS period. Just know that's go sub, and I'll point out some others where they get compressed, RET, return, etc. Question mark, print, although it stays question mark when you use question mark, which is nice. It makes it more compact. You can fit more things on a line. So in essence, as we go down, we see we've got all these basically it's reading through I figure out where the program is at. Peak 130, 131 is where the vars are, so that I get those first. Then the values are at 134, 135. And these are documented. It's a good time to bring this up since we're looking at such these strange memory locations. What are they? 120, 121 is going to be, where is it? Space 120 through 121. Yeah, it's here somewhere. So as you can see, I'm at a memory, here it is, 119, 120. So as you can see, I'm at something called Atari Archives. This is where you should go when you want to find things pertaining to the Atari, old documentation, old magazines, articles, type in code. Sometimes there's even stuff that's already been typed in, maybe disk images and things like that that came with magazines. Those you'll also find at archive.org. AtariArchives.org is more of a, definitely very much focused on this stuff. So this particular book here is called Mapping the Atari, and I'm looking right now at the memory map section of that. And it goes through every memory location, starting right down from 0 and going all the way through. And some of these are used by BASIC, and some of them are used specifically by the operating system, which is, there isn't much of an operating system, as you can imagine, on the Atari. And so sometimes it's tricky to figure out, looking through this, what is BASIC and what is specifically for the operating system or for parts of the system. There are things like your display list, for example. When you start up and it's got that blue field, all those lines of text, that's somehow built, and there's a bit of ROM code that creates that, but it's all in RAM so that you can modify it. And the reason it's in RAM is because the way these vectors work is they point to things. So you have, say, 2 memory locations, and there'll be the low byte and the high byte, and together they create a 16-bit pointer to someplace in memory. And so those are called vectors typically. So here you have DOSVEC, for example. Start vector for disk or non-cartridge software. The address BASIC jumps to when you call up DOS. So you can point to your own routine when you type the word DOS, it'll go to it. You can do some clever things with that. But that's particular to BASIC, so it looks like. So it looks like the kind of thing, you could reuse these memory locations if you weren't running BASIC and you didn't need to use the functionality that it's using. And since zero-page memory locations are special on the 6502, it's nice to be able to reclaim some of these and use them when you need them. So there's so many poke mask, break key. 0 means the break key is pressed. Any other number means it's not. It's monitored by the keyboard, display, cassette, and screen handlers. Is it a hardware register? It's a good question. Sometimes it's not easy to tell whether some memory location is being written to because it's connected directly to hardware, or it's got some routine somewhere that's changing it. I presume that this is the low-level keyboard routines are handling. There's an interrupt that's doing this and setting this particular flag, which is a whole byte used up. It could have been probably a bit, but it looks like it has some various values maybe. So then you've got real-time clock, 3 whole bytes for that, because clocks, it's nice to have, and they're 60th of a second, so it's good to have, enough space to keep up days and days of time if you need to. And with 3 bytes, 24 bits, 60th of a second, somebody else can add that up, but it adds up to a lot of time. So it gives nice listings here. Go to Compute August 82 for useful programs. So this book is, very much in conjunction with the other literature, and it borrows a lot from it. A lot of what's in these books is actually learned from magazine articles and things, corresponding to also the Atari documentation and people experimenting. So the memory location that I was looking at in here in my program was like 130, 131. So let's go down to that. I'll just quickly zip through. 130, 131, there we are. Beginning address of the variable name table. Variable names are stored in the order input into your program and in a ASCII format. So that's pretty cool. You can have up to 128 variable names. They're stored as tokens. So yeah, basically there's a number between 128 to 255. And when you find one of those as you're untokenizing your program, or when it's being tokenized, it'll turn these variables into them. They become lookups for the name, and then just sort of a stand-in for a value. And then the variable values are stored somewhere else. Depending on the type of variable, there'll be different values. So it continues to store variable names, even those no longer used in your program. Is not cleared by saving your program. Loading a new program replaces it with the one it retrieves from the file. Nope, you must list your program to disk and then use the enter command to bring it back in. So that's a nifty facet of the variable table, is because of the way it works. Like as you're messing around, even with in the command line, even if you're not typing in new lines, you may be creating new variables, just by syntax error, by mistake, and not realize it, and then you save it off, and it stays there forever, even as your stuff gets archived away. And only later on may it get, listed out and then removed again. So I try to store all my stuff as listings anyway, just because it's easier to edit them once they're in this format to, and they certainly, load and compile or tokenize very fast, so that's fine. So yeah, as you look through this, you can find that, and then there's the variable name table, or the ending address of the variable name table plus 1 byte is fvntd, and there's some reason I'm using that maybe. Yeah, so here I'm looking for 132, 133. And comparing. If I'm greater than or equal to that, then print, return. We're done. So yeah, as I'm going through this little routine here is actually just printing out the variable, I believe the names. Yeah, and then the next part prints out the values. So it's using 134, 135, and that shows you here a variable value table. Boom, and you can look them up. How is the format done here? What do the values mean? Is it, so it's a scalar, meaning it's a number. Is it an array? Is it a string? And so on. And so yeah, it's basically like any system you have to kind of like deal with. It is a weird setup. It's not like you can just type it in like JSON. These tokens are funky characters, and they're just bytes that have been picked out because maybe alphabetical order or other things. And just what happened to be built at that time became the token system. And you could imagine, as you switch tokens around or change the language or add new statements, you could move the tokens around, and pretty much, everything should be just fine. If you want things to be backward compatible, you'd have to keep the old tokens around and replace them with new ones, maybe shift them as you load them up or whatever. But yeah, if you could have a conversion utility or whatever. So you could imagine that sort of most people save their stuff in .bas format. So I don't know if that held things back from being upgraded and moving on to like newer versions of BASIC. But there actually were a few different variants of BASIC for the Atari, and some of them were add-ons for your basic, and some of them were real full new versions of BASIC that ran faster, that had support for integers, that allowed maybe easier assembly and things like that. Maybe even had a built-in monitor in them and things to make it sort of more integrated and make it more of a full environment. Working this way with BASIC isn't what I would recommend. This is sort of the way you start entering into what's going on and looking at the innards of what's going on in the Atari's memory. So this untokenizer, which is quite long, it's included with the AtariBASIC stuff. So you can check that out on my GitHub, and I'll keep updating it. Next thing I wanted to check out while we're looking at Atari memory locations and memory maps was the display list stuff. And so I have this dlist file, and to help us with that, there's another book which is called Day Ray Atari, also very popular in its day. And this was a little more in-depth. It actually not only had a bit of a memory map, less of a memory map I think than mapping the Atari, but and it may have even referred back and forth to that book. But it has an awful lot of good examples, little examples, and a lot of great descriptions. Kind of wordy sometimes, but definitely authoritative and different, and a lot of stuff to experiment with. So we're looking at display lists right now, and we're going to see something that looks similar to this here when I run my dlist program. So a display list, what is it and what is cool about it? Well, the Atari display system was a little more sophisticated than your 2600. It could display text, or what you might call postage stamps, because they're all the same size. But they're basically, it was meant to be ASCII format, and that's the bytes that are actually correspond in the font are aligned with ASCII. They don't necessarily have to be. You could make an entirely new encoding, move all the bytes around, change the glyphs around, and voila, you have an entirely new system. But it's aligned with ASCII, and so that's the format. But you can also, of course, redefine characters into graphical shapes and use them in interesting ways. And you can invert things. So if you drew something one way and you wanted to draw you needed to say draw the inverted, or you only needed the negative part of it, you could draw it inverted instead of making a whole new character. So in that way you could sometimes save space by having things be mirrored. But the display list was typically was set up so that it would actually define how things would be displayed, how bytes would be displayed as you go down the screen. And you could specify this line is going to come from this place in memory, and it's going to be 40 bytes long and display, characters. You could even get rid of the overscan, and then it could be 48 bytes of characters, and then you could do some scrolling and do other tricks with it. And each line was like that. So if you needed to have 10 lines of characters, you actually had to have 10 number twos, which are what you show here. Number two being the basic 8 by 8 small square um, characters that fit on the 40 by 24 screen. So that's what these lines are, these twos here. And then there's like, little commands inside these display lists, like you could say jump and wait for vertical blank, as you see down here at the bottom, which basically means I want to set the display list pointer to this memory location and then wait for the vertical blank, and then it would basically wait for the screen to finish. And the display list program was running it on its own as a little tiny program on a separate chip. So you could think of it as being a little program that would run and in correspondence or in hand with the display chip as it finished one set of lines, like your character line. You could then have something immediately after in your display list, and it would be evaluated at that time and get ready for the next line. And so you could insert little things too. You could have like, I want to do a vertical blank interrupt at this point inside my display list, or not a vertical blank, but just an interrupt, a display list interrupt, they call them. And you could just say, I want to do a DLI now, and you could call that code or whatever it might be. And so maybe that code would be, sometimes it was something just like change the color, but oftentimes it would be fairly sophisticated. Change the color and do the other player logic or something like that even. You don't have much time there, so maybe the player logic would have to be very simple, but you could do little slices of player logic for each line if you wanted to, and things like that. And there were other ways to do interrupts and have timers, but tying it to the display was a really good way, because you were guaranteed to get that 60 hertz timing or that 50 hertz timing if you were in PAL regions. And so pretty cool stuff. If I run my program, what's called dlist.lst, it doesn't do much. I just have it start out, and it prints out some memory locations. So VDSLST is just like, the only one that matters really is like the last one, SDLSTL. That's the display list pointer. That's where this display list that we're looking at now resides in memory. And if I hit space, you can see it's now 39968, and now it's 38944. Well, what did I do? If you look carefully, I also changed memtop, and I should have pointed it out, from 160 to 156, lowering it by 4. And then I changed the graphics, which is why I cleared the screen, graphics 0. And then, yeah, it's a bit long. Let's run it again. So here you see it's 156 memtop. SDL/STL is pointing at 38944. If I hit space, now it's 152 37920. So again, each time it's going down by 4, and SDL/STL is going down by 1024. If you don't do the math, you don't have to do the math. I'll do it. It's 1024, which corresponds to 4 pages, each one 256 bytes. So memtop is memory location 106, and it specifies where basically the highest location that should be allocated and used for stuff. And so the display list is typically stuck up there. So what you do is, when you want to set aside memory inside BASIC and utilize it for your own stuff, you subtract however many pages you need from 106, and then you do a graphics shift, change, graphics 0 in this case, and then voila, you now have that space you can use. And so if I want to play around now, I can use anything above in that area, 37920 plus 1024, and I think I did it twice, so I've got a whole 2K up there that I could throw display list into or whatever. But what I'm actually going to do is also change one thing, which is remove line 100, and then run this, and we'll just look at the display list, which is what this code actually does when I have that line in there. It tells me that the display list is at 37920, which is correct. You can see it's SDL/STL. The first line is 112, which means skip 8 lines, and then it's got 3 of those more, and so that's where you get that black bar at the top of the screen. And then it's got text 0, which is 2, plus LMS, which is 64, and it's basically telling it that you should start a text line, and here's the address that I want you to use for that text. It starts at 9440. And then so the next line and the next 23 lines after that are all just plain old 2, which just continue to display that memory as text. So if I were to do a poke of, say, 9440, I should be able to affect what's on the screen. So let's try that. Poke 9440, let's put 65 there, which should be an A, right? Oops, I scrolled the screen, so it didn't work. Hey, that didn't work. Let's see what I do wrong. Oh, you know what? It's hexadecimal. So it's 37920 plus 32. 37920 plus 32, 42, right? 52. 37952. 37952. There, I know my math. So there, hey, something showed up. Okay, well, 65 ASCII, well, actually, it turns out that the codes on the screen are a little different. If I poke 1 there, it should be an A. Oh, no, wait, 1 is exclamation point. They're 32, shifted by 32 or something? Now I can't remember, so is it 33 is A? Yeah, okay, so they're shifted by like 32 from ASCII, but they have their own order. So now if I do the same with the next memory location, hey, there's an A at the top of the screen. Look at that. So yeah, so this is actually displaying memory. So let's make that into 0, and 0 is space, whereas 32 would ordinarily be space in ASCII world. But 32 here is an at symbol, which again is normally 64. So it seems like it's off by 32, but I know it's not exactly. That's not exactly right. We could run a little program to poke all those memory locations and see, and that would be interesting. The cool thing is, like, even if it prints a clear screen symbol or whatever, it won't clear the screen. It just puts the character there, whatever it might be. So let's do a quick little loop, and we'll put that there. For I equals 0 to 255, so we'll put all the characters. We'll do poke 37952, 37952 plus I, next I. There we go. There it goes. All right, all the characters, there they are. So you can see that's the order that they naturally are in raw byte form, I guess you'd call it. And you can see there's 256 of them. And yeah, there you are. Pretty cool. So you can point the display list here, which is at 9423. I could point it to a different memory location, and it would totally suddenly shift, but then also what would happen is you wouldn't see my cursor moving on the screen. One thing I will try, which will be fun, is we'll try going to 9426 plus something. So 37920 plus 6 plus, we'll go down, say, 10 lines. 37920 plus 6 plus another 10. 37936. So let's try that. Poke 37936, where that, which is actually part of the display list itself, I'm going to put a 0 in. Let's see what happens if I stick a 0 in the middle of the display list. Oh my god. So what's happened is that one of the lines disappeared, the screen became shorter, although the cursor can now go off the bottom because it still thinks that it has 24 lines. But if I go up here, oh, look at that, it jumps right past that. So it's as if that line doesn't exist. But it has a 0 in it, so 0 must be doing something. And as it turns out, 0 is a command that does do something. I forget what it is. Let's put 16 there. Oh my goodness, 16 is taller than 0. What about 32? it gets taller still. So I think this is a case of like 112. I know 112 is skip 8. 0 must have been skip 1 or 2? It looked like 2, didn't it? Let's put 112 there. And see, there's that big skip 8 hole lines. It looks like an entire line is missing there, but it's actually as if nothing is there. And what I've told the display to do is just skip. So in fact, there is nothing there. It's a void. And so you can use this sort of thing to mess with, your screen and create neat displays for games and things. There's also, well, I mean, if I were to go through this whole list of all the things this could be, I mean, there are so many. Let's try 3. Okay, that didn't do much. Let's try 4. Oh, look, 4. 4 is like a weird, colorful mode where inverted characters have a change one of the colors to a different color. That's pretty cool. That's neat. So let's take another look down here at 5. 5. Oh, 5 is a tall one. Yeah, so as you go through, you eventually realize or learn that what these are. You can look them up, but yeah, each one is a different mode and they're different sizes, and yeah, and they look different depending on whether they're inverted or not. So that's pretty cool. So let's go back to 2. Hey, we're back to normal. So that's display lists, the essence of them. It really is quite straightforward. The last thing, of course, at the end is that 65, which is wait for vertical blank. Jump and wait for vertical blank plus LMS, so that's that 64 again. And it means include an address for that to jump to. And that's what that does. So that's pretty cool. Now, I've done some pretty sophisticated things in the past with display lists, but I'm not going to get too into that this time around. I'm just giving a basic intro and giving you a basic idea of what can be done. So if you go to a graphics mode like 2, which is actually a text mode, I believe, if I'm not mistaken, I can actually say print number 6, because I think that's by default is the screen. Hello. And it puts it up on the screen. Oh, I put a comma in, which is why it's tabbed way over. So if I were to put a semicolon here, see, now it's on the left. So each time I do that, it does it. And I believe it will never scroll, though. Like, it'll keep doing this, but it'll just get down to the bottom, and then it'll fill it. And it's not like the regular text screen that we're using now. Yeah, see, now it's actually saying error 141 because the cursor has gone beyond what can be printed. So there's actually limits on what you can do with this mode in terms of printing, but you're meant to use it a lot for character graphics, and you can do some pretty clever tricks. Even in this chunky character mode, you can do some really neat looking things, and people have made games in this mode alone just using this and clever color changing and other stuff. But yeah, this is again another display list, and if I were to run my display list program, you won't be able to see everything, but here it says that it's at 38488, and then it says 96, and it says error 9, and probably because when I first wrote this, I was only writing it for this demo to do basic display lists with 2 in it, so it doesn't know what to make of 96. So I'll finish it up next time for another review. So what I want to do next time around is get a little more in-depth, a little more sophisticated with these display lists, play around with them some more, show how you manipulate them and how you can do some tricks, and we'll get into some actual assembly language and play with them in that realm. It'll give us a chance to look at ways of programming assembly language, which I'm going to do mostly from Sublime, just using build and single files, so it'll be pretty straightforward. Then I hope we'll get a little more into CC65 and program some C and see about how display lists are done in C. Now there's a lot of really good demos out there on the web already, a lot of good YouTube videos, but some of them are a little old, and it's always good to have fresh content. And I know I'm learning as I go, and I'm going to be trying to revive some things, and maybe we'll jump into a project and actually build something. I think that'll be maybe more interesting than kind of randomly poking around. It'll give us a chance to actually utilize Day-Ray Atari more. Let me bring up the front page of it while we're talking. And here it is. You look at all these. Look at this contents. There's just so much to it. How to do vertical motion, horizontal motion, color registers, character sets, player missile graphics. We're going to get into that. I didn't want to get into it too much this time, but display lists and display list interrupts, hardware collision detection, playfields and priorities, like things can be in front of and behind each other. All these things that are built into the Atari hardware that are just astounding for such an old and relatively cheap piece of hardware for the time, and one that stuck around a lot. I mean, the essence of the 5200 and the 7800 was, basically just the Atari computer with not much added to it. It stuck around for a really long time and then became the sort of the sole grandfather of the Amiga, built by the same guy, J Miner. So there's and then here's, look, we even get into the tokenizing process is even described in detail in Day-Ray Atari. I mean, it gets down to the nitty-gritty. And if you remember my last retro, I gave a brief intro to the things I'm working on and the tools that I have. And one of those things is going to be a tokenizer and also a detokenizer. So basically just to have them and to have things be faster for going straight from Sublime to boom, immediately be able to run it. Base files are much smaller and they don't need all that parsing, so it definitely is going to work a lot faster. And it'll be a great exercise. So we'll get more into that as well. And I'm going to keep you apprised of that. I'm doing basically spending not most of my time still on the Marlin project, and I will always be doing that primarily. But I'm putting in a couple hours, at least a few a week to get more into this. I have the Commodore 64 on hand, but I'm not going to be playing with this too much yet. I have there are different ways you can deal with these, and I've got a FPGA based board maybe coming, so we're going to look into that. We'll look at that when it comes. I did mention last time that we were going to look at Dino Wars. This is more in the Amiga realm than the Atari realm, so we'll look at Dino Wars when I get around to that Amiga stuff and that part of history, and we start looking at some of the essence of Amiga. Again, I don't have much of the source code from that era, but I think that if we poke through some of the examples that we find, we can learn some things and see some interesting parallels to the Atari. They both have a similar display list concept, but the Amiga's is more sophisticated, but what's interesting is that you can do some of the tricks that the Amiga did with its more sophisticated hardware on the old Atari, and it would, like multiple screens that you could drag up and down, could have been done with if there had been a mouse, that was standard on the Atari. It just wasn't a thing. But it would have been something you could have done, and if you built more memory into it and made it into a behemoth, made a giant Beowulf cluster of those things or whatever, they could have been something amazing. But given that the Amiga was the spiritual successor to the Atari, and unfortunately didn't catch on too much in the States, could have probably beat out the Mac, could have beat out the IBM PC, but it just didn't have, I think, I was talking to somebody about it recently, and thinking about it was like, yeah, probably desktop printing, like, publishing, laser printers was probably the killer app for Atari, and of course VisiCalc being the really killer app for IBM PC. And there really wasn't, the killer apps that we had for the Amiga were Deluxe Paint and the Video Toaster, and they had their niches, but unfortunately it just wasn't the sort of thing that made it take off. And well, we'll explore that more in the future. So I'm going to sign off now and go have a burger, but I wanted to give you that brief intro, give you some ideas about how if these funky old pieces of hardware just would, make up their own ways of doing things. So there is this, sophisticated display list thing baked into the hardware, and it's pretty cool. So I think it'll be fun to explore it more and play with it more, and see what we can do with it, and see how maybe explore some games, and look at how maybe they did their display lists, and explore what they have in them. But we'll get more familiar with the display list contents and the actual values, what they do, in the next installment. So thank you for dropping by, and I hope you'll all remember to like, share, subscribe, leave your comments, and I'll see you next time. Ciao.